Question 22 from Section 1 of the 2019 National 5 Physics Examination. For a particular radioactive source, 1,800 atoms decay in a time of 3 minutes. The activity of the source is, and you're given your 5 choices. Go straight to the relationship sheets and we can see all the equations to do with radioactivity. And it's the top one. The activity A equals n, the number of decays, divided by the time which the decays took place in. So the equation we're going to use equals A equals n divided by t. So write that down. So the activity is going to equal to the number of decays divided by the time. So we had the following. We had 1,800 decays. I'm going to divide that by the time, and be careful, it's 3 minutes, but we have to convert that into seconds. So it's going to be 3 times 60. And that's going to give us 1,800 divided by 180. So if we do our cancellation, we're going to end up with 10, and the units for activity is the becquerel, BQ. So our answer is going to be 22A. Question 23 from Section 1 of the 2019 National 5 Physics Examination. The crew on an aircraft during a transatlantic flight are exposed to cosmic radiation at an equivalent dose rate of 5 microsieverts per hour. The crew complete 6 transatlantic flights each month. The average duration of a flight is 8 hours. The equivalent dose received by the crew during the cosmic radiation during the transatlantic flights in 1 year is, and you're given your options. Go to the relationship sheets, and the equation we're going to use is that bottom one. It's the equivalent dose rate. Remember, H dot is the rate of something. In this case, it's the equivalent dose rate, and that's equal to the equivalent dose divided by the time. So starting from that equation, we can work our way through all the times. So let's start then. First of all, we have our equation, and our equation is H dot, the dose equivalent rate, equals H, the equivalent dose, divided by the time. So we rearrange that, we can have H, the equivalent dose, is equal to the equivalent dose rate times the time. So let's take it one step at a time. Let's put in first of all the dose equivalent rate you received during the flight, and that is going to be 5.0 microsieverts, and it's going to be per hour. I'm going to multiply that by, first of all, we've got a flight time of 8 hours. So 8 hours will give us the equivalent dose for one flight. But we have 6 of those flights in a month. So we've got to multiply it by 6. And we have 12 months in a year. So that's a calculation we're going to be using then. So we do that in a calculator. We have 5.0 times 8 times 6 times 12. And that's going to give us an answer of 2,880 microsieverts. So the equivalent dose that the crew receive from a year of flying those transatlantic flights is 2,880 microsieverts, and that's going to be answer 23E. Question 24 from Section 1 of the 2019 National 5 Physics Examination. A radioactive tracer is injected into a patient to enable doctors to check the function of a patient's kidneys. Radiation from the tracer is monitored outside the patient's body by a detector. Which row in the table below shows the most suitable type of radiation emitted and the half-life for the tracer? Well, key fact number 1 then. Alpha and beta radiation cannot penetrate the body to the detection camera. So you can't use alpha and you can't use beta radiation. Only gamma radiation can pass through a body to the outside detector. So you're looking for gamma radiation. So that's going to be either this response here, D, or response E. Now, the other key thing about tracers is that the half-life of the tracer, it must be short enough not to stay in the body too long. So we're looking for something at hours rather than years. So a response looks like it's going to be D. So type of radiation emitted, gamma, half-life of the tracer about 6 hours. So 24, answer D. Question 25 from Section 1 of the 2019 National 5 Physics Examination. The activity of a radioactive source is 56 megabecquerels. The activity of the source 40 hours later is 3.5 megabecquerels. The half-life of the source is, and you're given your choices. So to do this question in half-lives, we start off with the initial activity, which is 56 megabecquerels. And we'll just leave out the megabecquerels for the moment. And to get this answer, we're just got to keep halving that activity until we get to 3.5. So half of 56 is 28. Half of 28 is 14. Half of 14 is 7. And half of 7 is 3.5. So there we have our final activity, 3.5. Now let's count the half-lives. We had 1 half-life, 2 half-lives, 3 half-lives and 4 half-lives. So 4 half-lives of that source is going to equal 40 hours. So 1 half-life, well, that's going to equal just simply 40 hours divided by the 4, which is going to equal to 10 hours. So the half-life of this particular radioactive source is 10 hours, and the answer will be 25B.